So as I mentioned earlier, the objective of today's class is just focused on practicing the second law and entropy. Therefore, without further ado, let's jump into the questions. And in today's session, I have one small request for all of you. Please try to solve these questions with me. And if you find challenges, then you'll see. Because whenever somebody else is solving a question, it looks so easy. And I tell you, when it is going to be you who's doing all the calculations, then it's not going to be that easy. Therefore, let's all work together in today's class and see what are the challenges that we face. Okay, take about 5 to 6 minutes and try to start the solution process and progress as much as you can on this question. Okay, let's start the discussion now. So the question says there's a furnace which can provide heat, amount of heat of QH1 at TH1 temperature, and it is used to drive a Carnot heat engine. So we marked QH1 and TH1 here, and it is used to drive a Carnot heat engine. The best thing or the characteristic of Carnot heat engine is it has the highest efficiency that can be held or by a given heat engine, right, under the given conditions. Under between TH1 and TATM, Carnot heat engine can produce the highest work. Okay, so that is the specialty about the Carnot heat engine. And then while working, Carnot heat engine rejects heat at atmospheric temperature, so we mark that one as well. And then the heat engine drives a Carnot heat pump. The work coming out of the heat engine, W, is used to drive a heat pump, right? So heat pump absorbs heat from the atmosphere and eject it to room temperature, and the amount of heat removed or added to the amount of heat added to the room is QH2. And the question asks, it want to find QH2 over QH1 as a function of temperatures. So when it comes to this problem, first of all, can you understand how we came across this figure? How to develop this figure? Anything not clear? Or are we all clear about what's going on in this diagram? Anybody? So Alan, do you understand this is how we draw a heat engine? Is it clear up to that point? Perfect. And the work from heat engine is added to the heat pump. Are you clear? Like, this is how a heat pump is drawn. Okay, so that is all you need to know, because the question is asking the ratio between QH2 and QH1 as a function of temperatures, right? So there are QLs, if it is the question, QL1, QL2. So there's no expressions given for that, right? So if that is what you are worried about, there's QL1, QL2, but it's like some values are given in a question, some values are not given. So QL1 and QL2 was not given, so we are not going to use that in the question. For heat pump, the lower temperature is to room temperature, high temperature is TH1. For a heat engine, the room temperature, sorry, for heat engine, so heat engine portion, high temperature is TH1, low temperature is T atmosphere. Okay, and for the heat pump, room temperature is the high temperature, and sorry, yes, room temperature is high temperature and surrounding temperature is the low temperature. Did I answer your question, Alan? Awesome. Now let's try to see how we can solve this problem, right? So it wants us to derive a relationship between the QH2 and QH1 using the temperatures. And we don't know exactly a relationship between these two parameters straight away, but we know that for heat engine, thermal efficiency can be written as useful work in the heat engine is W, and the work input or energy input is going to be QH1. And at the same time, for a Carnot heat engine, we know that it's going to be 1 minus TL over TH. Okay. Are we clear up to this point? Anybody having trouble understanding the equation 1? We defined the heat engine efficiency for a general heat engine, but we in the question it says it's a Carnot heat engine, therefore we know that it satisfies this relationship as well. Okay. The ratio between these two, considering the absolute values, yes, that's a good question. So anyway, these are going to be QH1 and QH2 going to be considered to be no, yeah, you're right, absolute values, right? Did I answer your question, Desa? Okay, so now for heat pump, we know that we don't define efficiency for heat pump, but we define COP. COP equals useful work in the sense of a heat pump is QH2, and the work input is going to be W. And we know that for heat pump, the COP can be written, for a Carnot heat pump, the COP can be written as TH over TH minus TL. So equation 2, right? So now when we are looking at these two equations, we can see that only W is the unknown parameter. Everything else is given in the question. And if we want to get a ratio between QH1 and QH2, then we can substitute from equation 1 in equation 2, or we can substitute in equation 2 in 2 using equation 1. So vice versa. You can go both ways, right? You can basically substitute for W in one equation using the other, so that you come across the answer. So anything not clear about this solution? Anybody having issues understanding it? Any challenges? So for sorry, here there's some typo. This should be TL divided by TH, and for TL and TH you have to substitute, right? Let's go to the next step, next page, and then it has the answer. Okay, give me one second. Okay, so for heat engine, for the heat engine, thermal efficiency can be written as this, and there the low temperature or TL is going to be the atmospheric temperature, and high temperature is going to be TH1. And for heat pump, the high temperature is going to be the room temperature, and low temperature is going to be the atmospheric temperature. So we substitute for these two expressions using the temperature values we already have. And then from this equation, like when you're looking at the solutions, you will see beta. This is same as COP. Okay, so Some people use, some textbooks use beta as the COP, but in the exam you won't see it, so you can use COP directly, right? Anything clear? Everything clear? Everything clear up to this point? Anybody? Perfect. So when we are looking at this problem, it shows us another thing. Okay, so if beta prime nn or CO Q, we can write QH2 equals COP into thermal efficiency of the heat pump, heat engine into QH1. Okay, so if this number is greater than 1, COP into thermal efficiency is greater than 1, then it says that QH2 is greater than 1, and QH2 is greater than QH1, right? If COP into eta greater than 1, QH2 is greater than QH1. Do all of you agree with this statement? Perfect. So what does that tell us? If we use the furnace straight away to heat our house, then our house is going to get QH1 amount of heat. And as we use our new setup by using that heat to drive a heat engine, then to power up a heat pump, then there we gain some energy, right? So QH2 is greater than QH1. So if we were to assess these two systems, two approaches, would you pick the setup proposed in the question, or would you rather heat your house using the furnace straight away? We'll use the setup, right? Because it produces more heat than we input. Basically, if we just use the furnace, assuming 100% efficiency, the maximum amount of energy that we can receive at the house is going to be QH1. But using our system, the heat received at the house is going to be QH2, which is greater than QH1, if COP into thermal efficiency is greater than 1. So basically, you assess this parameter, and if this component is greater than 1, then definitely we are going to use this system, right? Any questions so far? W dot and QH dot. So if it is given in the rate form, so you can use the rate form or the absolute energy form in a efficiency equation. The only key is if you use one component in the rate form, the other components has to be in the rate form. So that is the thing. Okay. Okay. Now let's move on to question 2. Take about 5 to 8 minutes and try to answer part A. Okay. In this question, it says a heat pump heats a house in the winter and reverses to cooling mode in the summer, right? So this is one advantage of using a heat pump. It can be used to both heating and cooling purposes by reversing the cycle. In the heating mode, we uh, apply or add heat into a given house. In a cooling mode, we remove heat from a given house. So that is the idea, right? So in a winter month, our priority is to heat the house. In a summer month, our priority is to cool the house. So depending on that, we can pick which mode we want to use our heat pump, right? So the interior temperature should be 20 Celsius in the winter. Okay, so the first part is about a winter term or winter month. So we know that according to the question, the interior temperature T room 1, let's say TR1 equals 20 Celsius. 20 Celsius, and that means 293.15 Kelvin, right? So now we know the temperature inside, and the summer 25 Celsius. Okay, heat transfer through the walls and ceilings is estimated to be 2400 kilojoules per hour, and per degree temperature difference with the outside. Okay, if the winter outside temperature is 0 Celsius, okay, outside, T ambient, so we'll say T out 1, T out 1 equals 0 Celsius, or we can say 273.15 kelvins, right? And then Q leak, the rate of heat leakage is given. Q leak equals delta T into 2400, right? Delta T is going to be T out minus TR1, so which is going to be T out minus TR1 into 2400. So that's going to be 20 into 2400. Any problem up to finding the Q leak? Everybody clear so far? Everybody clear so far? Awesome. So now, can anybody say that if Q leak is 20 into 2400, what can you say about QH? If you want to maintain this building at the same temperature, what can you say about the QH and Q leak? Should it be equal or greater than this thing, or what is going to be the number? Q leak and QH. Perfect. QH equals Q leak. It should be. Otherwise, if we could not provide the amount of heat that is lost by the building at a given time, then we cannot operate the building at the same condition, right? Very good. And therefore we know that this is Q leak is equal to our heat input from the heat pump. Okay, and then we know that beta prime, if it is not familiar to you, like COP is equal to QH divided by W in. The heat is given in the rate form because the information we have is per hour heat loss from the house, right? And then W in is not given. It asks for the minimum power, right? Minimum power. For a heat pump, when do we get the minimum power requirement to produce a given heat? When do we get the minimum power to produce the given heat? In simple terms, if it is a reversible device, or in other words, if it is a Carnot heat pump, then we can get the best work output for the given input, right? So then we only need a relatively smaller work input compared to any other heat engine operating under the given conditions. That's why we assume that this is going to be a Carnot heat pump if we want to get the required heating at a minimum work input. And then with that assumption, we can say that the COP of a Carnot heat pump can be written as this: T high divided by T high minus T low, right? The high temperature is inside the house, which is 20 Celsius, and then we substitute in Kelvin. Very important. In Kelvin, if you substitute TH in Celsius, you are going to lose marks, and that is wrong as well, right? And then TH minus TL, that is going to be the difference between the two temperatures, which is 20, right? So you substitute there, and then you know the efficiency, you know the heat input, and from that you can calculate the W in requirement, kilojoules per hour, right? So if you want to convert this answer to kilowatts, what you do is 3275 kilojoules per 3600 seconds. So once you solve this portion, you'll see that the answer is 0.91 kilowatts. That's how you convert kilojoules per hour to kilowatts or kilojoules per second. The same thing. Kilojoules per second means kilowatts. Okay. Anything not clear about this portion? For both example 1 and example 2, talking about driving a heat pump would be used, okay, in watts. But why this is not the case for example 1? Alan, if it is in a rate form, then it is kilowatts or watts, because watts is a rate form, joules per second or kilojoules per second, right? The same idea. If it is not in a rate form, then it will be kilojoules or joules. That's the thing. We can either use the rate form or we can use the total energy to do a given process, right? It's more sensible to use the energy requirement per given time. Therefore, in this question, it uses kilowatts. It says heat engine was driving heat pump. Okay, let's go to the question itself. So what is the problem here? Now, heat engine is the one produces the work input required for the heat pump. So it could be anything. So if you are clear about part A, take another 2 minutes and try part B. So in this question, it says for the same power as in part A, right? So for part A, we know that this is the power input, right? 0.91 kilowatts. For the same power, what is the maximum outside summer temperature for which the house can be maintained at 25 Celsius, right? So we know that in a summer month, what happens is the heat is entering our house automatically because it's so hot outside and our houses are getting hotter, right? So unlikely in the winter months, what our preferences would be to remove heat from the house rather than adding more heat. We are interested in removing some of the heat so that we can maintain it in a good condition to live, right? So in a summer month, Q leak is going to be delta T into 2400, as same as in the previous question, right? So in this delta T, the outside temperature we don't know, so it's going to be T house, so we can pick to be house at the given condition, and T out minus T house into 2400, right? The temperature of the house is known. It is 25 Celsius. right? So we don't know the T out yet. We don't know the T out yet. Therefore, we can write the Q lead to be 2400 into TH minus the outside temperature, inside temperature, sorry, inside temperature, right? Similar to the previous example, if we want to maintain the house at the given condition, then we should remove an amount of heat which is similar to the amount of heat entering into the house. That's why we can say that QL in this heat pump is equal to the Q leak, right? Are we clear up to this point? Perfect. Now, again, from the COP equation, COP, we know that the COP can be defined by the useful or desired output. In this case, the cooling effect is the desired output, right? Therefore, we can pick QL divided by the work input W in, right? So QL, we have an expression already, this one, and then work input is same as in the previous question. So this is going to be our work input. So this equation, it is very straightforward. And it asks what is the maximum outside summer temperature for which the house can be maintained at 25 Celsius, right? So this maximum outside temperature means that is the summer is going extreme and extreme, right? More heat leakage into the house. So if we have the best efficiency only, then we can go for the maximum load and give the maximum cooling effect. Even in a hotter summer day, we can maintain our 25 Celsius temperature, right? Therefore, the maximum temperature difference can be catered using the given work input only if we use the Carnot heat engine, right? And when it comes, Carnot heat pump, sorry. When it comes to the cooling mode of a Carnot heat pump, the COP can be written as this. And we can substitute from the known values. We know the house temperature, so we plug the house temperature, but we don't know outside temperature, therefore we leave it as is. And when we are substituting in any of these, I reiterate, we have to use Kelvin everywhere, right? So if you use Celsius, then we will be in trouble. So when it comes to second law calculations like this, efficiency, COP, whatever of Carnot engines, or entropy calculations, the ratio between Q and temperature, use temperature in Kelvin scale. Okay. So are we clear up to this step? Anybody having difficulties understanding this portion? Awesome. And with this equation, we can get this solution. So it's interesting to note TH minus 298.2 squared equals the right hand side portion, so which is going to be about 108.72, and when we take the square root of both ends, we get TH equals, sorry, I will write TH minus 298.2 equals plus or minus square root 108.72. What do we pick? The plus or minus value. So when we look at this number, this is going to be our TL value. And if we subtract something from the TL value, then it's going to be lower than TL, right? But TH should be always higher than TL. Therefore, we can pick the plus value, right? So we can use the logic produced by Dacer or this logic. Either ways, we have to go with the plus value. And that's why we come across the plus value and get this number. Don't confuse the thing with the name here, because the heat pump operating in the cooling mode in this one, Alan. Okay, because the desired input, like that's why I always pick the desired this desired thing out of this thing is the cooling effect. When it is the cooling effect, this is operating as a refrigerator, almost, not almost, it's a refrigerator. It's going backward in the cycle. So let's take about 6 minutes to try and get a hold of this question. So this is again a combination of heat engine driving heat pump, takes waste energy at 50 Celsius. So the waste source is at 50 Celsius, right? So that means, sorry, take another color. That means the temperature here is at 50 Celsius. And again, waste source is here as well. So we can pick the temperature to be 50 Celsius in both places. And the heat engine absorbs QW1 amount of energy and it rejects heat at 30 Celsius. It is already marked in the figure. And QW2 goes into the heat pump that delivers QH at 150 Celsius. If the amount of energy absorbed from the waste is 5 megawatts, okay, so what does that mean? Amount of energy absorbed from the waste. So waste source is used in two places. Therefore, the total amount of energy absorbed is going to be QW1 plus QW2 equals 5 megawatts. This is 1. Okay. Find the maximum rate of energy delivered to the high temperature. So we are asked to find QH max. Sorry. QH max. This is the question asking. This is what the question is asking. All right. Are we clear about the question, what it is trying to do, what it's trying to ask from us? I hope everybody is in understanding. Awesome. So when it says maximum heat output to the high temperature, we know that the maximum heat output for a given work can be produced by a Carnot heat engine, Carnot heat pump, sorry, Carnot heat pump, right? So therefore, we know that the right-hand side, the heat pump that we see here is going to be a Carnot heat pump if we want to achieve the maximum heat input at the high temperature, right? And again, we know that only a Carnot heat engine can produce the maximum work under the given conditions, under a set of given conditions. Compared to any other heat engine, Carnot heat engine would produce a maximum work. So it's important that we produce the maximum work, and for that work, we eject the, or we add the highest amount of heat into this high temperature. So in this case, it is clear that both these devices have to be following Carnot cycles, Carnot heat engine and Carnot heat pump. Okay, are we clear about that? Are we all clear about that? Perfect. And now now it says it asks us to determine the QH, maximum QH, right? So maximum QH, we know that we agreed it's going to be the Carnot cycles. Therefore, if we consider the heat engine, efficiency can be written as W output is the desired work and QW1 is the heat input, and then we can write the same thing as 1 minus TL, sorry, 1 minus TL over TH. So TL is going to be, in this case, 30 Celsius. 1 minus 30 plus 273.15. It's very important we substitute in Kelvin, and then we divide it by T high, 50 plus 273.15. Right? That's the second relationship. Now we have an efficiency value. We already calculated that, and W we don't know, and QW1 we have it. Right? So as we have the efficiency value, let me write it in a different format. QW1 is equal to W divided by thermal efficiency, which we know already, right? And we are clear with the relationship too. And if we think of the heat pump of this system, then we know that we can write COP divided by COP equals desired output. Desired output is going to be QH divided by work input, which is W, right? And then we have this relationship between W and QH, right? So we can write W equals QH divided by COP. This is third relationship. You know that you can always calculate the COP of a heat pump using the temperatures, and I'm not going to redo it in this stage, but like in the complete solution, you can see that how it is being done, right? And then in addition to this one, we can apply the first law equation to the heat pump. Why do we apply first law equation to the heat pump, not the heat engine? Because we are not interested in QL, right? We want to find QH, and we know relationship between QW1 and QW2. We know relationship, we know the sum of these two, and we want to find this one. Therefore, finding another relationship between these parameters is going to be beneficial. So first law to heat pump, then we can say that QH, or else we can say that, yeah, QH equals W plus QW2. This is going to be the fourth relationship. If you solve these four relationships, then you can find the answer for QH. What we are interested in is finding QH. Okay, so basically my solution process for this one, if I have this question and if I have this equation in my hand, set of equations in my hand, what I would do is I will substitute for W, because W is not something we are interested. We don't know W, and at the same time we want to calculate QH. So from 4 and 3, I will substitute for W in this equation 4, right? And then from 2 and 4, I will get QW1 plus QW2, which is equal to 5 megawatts. So if I can have that set, then I will be left with all the known parameters to calculate QH. Okay, so let's look into the solution as well. So we can calculate the Carnot efficiency, and we can calculate the Carnot COP as well, right? Oh, sorry, not this one, the value. And in addition to the efficiency numbers, we have the relationship with respect to QH and W. So we can take these two relationship as well, right? And from these equations, we can apply the first law equation here, This is what I did in the previous slide. And from 1 and 3, we can get this relationship, right? Then with this one, we substitute from equation 2 for W, and we omit the W component from the equation by substituting by QH divided by COP relationship as seen here. And you know that QW1 and QW2 equals 5 megawatts. Therefore, we can write that this relationship stands. And from this, it's just a matter of substituting numbers, and then we come across the final answer. For any of you who want to solve this question, I will wait another 2-3 minutes so that you can go through the solution process. Why we don't use Q dot, since we are talking about rate energy in this case? That's true, Alan. It would have been accurate to use Q dot, right? The rate form. It's definitely talking about the rates. So when you are substituting the numbers, you have to keep in mind. And symbols, I would not deduct marks for not having the dot, but that's a valid point. Let's look into example number 4. So please note that this kind of questions can be in your exam, because this level of complexity you should be able to handle. Okay, so when you are practicing, pay attention to systems like where few components are combined and working together, and how to interpret the flows and everything. The first challenge of this question is what would be an appropriate system boundary? Do we need to assess the individual systems, or like can we straight away jump into the whole system and consider the inlet outlet flows? What would be the best way to go, whole system or individual systems? So I would prefer to go the whole system, because it asks to find the entropy generation. It asks us to find the entropy generation and say whether this process is feasible, right? So if we can assess the whole system, if we draw the system boundary like this, and then if this system is feasible, the entropy generation of this combined system is feasible, then we can say that, okay, it's feasible. It could be right or wrong, like, I mean, there could be a system like this or not, but according to the second law, we can say this is feasible, right? So now, what do you guys think? Is it sensible to use the whole system? Like, it's easier, right? We can always use the individual systems, but it takes more time. Let's go through the question together. A refrigerator uses ammonia as the refrigerant. Okay. A turbine that uses ammonia as the working fluid is used to cater the work input required by the compressor of the said refrigerator. Okay, now this turbine drives the compressor, right? And then it says pressure and the temperature of ammonia at the turbine inlet are 2 megapascals and 70 Celsius. Okay, so turbine inlet conditions, P1, T1, P1 is given as 2 megapascals, T1 is given as 70 Celsius. Okay, and then ammonia at the compressor inlet is saturated vapor at minus 20 Celsius. Okay, compressor inlet is here, so that is saturated vapor, and then temperature T3, sorry, T3 is given as minus 20 Celsius. Okay, the exhaust from both devices are at 1.2 megapascal pressure. Okay, so that means if both exhaust are at the same pressure, the outlet pressure or pressure at 0.5 should be the same, 1.2 megapascals, right? The ratio between the mass flow rate entering to the turbine, so that is M1, and the total exit flow was measured to be 6.62. So that means mass flow entering into the turbine is 0.62 into M5, right? M5. And whether this can be true, calculate or check whether this is true or false by calculating the entropy generation. So we need to find the entropy generation. Assume the compressor and the turbine both adiabatic. Okay. So now there's no heat output. Q equals 0. Right? And for the whole system, if you try to write the entropy balance equation, ds by dt equals Q over T plus, sorry, sigma m in entropy taken in minus sigma m exit entropy exit plus Sj, right? Assuming steady state conditions, we can make this 0. Assuming, sorry, steady state. Right? And then the question itself says that there's no heat transfer. So from this equation, we can see that the entropy taken into the system should minus entropy taken out of the system plus entropy generation is equal to 0. So from this equation, we can find entropy generation. Okay. Okay, we have one question. Let's see. Sorry, you cut out for me. Why can we assume steady state again? Okay, so steady state assumptions like for turbines, compressors, such devices that we are analyzing in this course, we are always going to consider the steady state. Transient operation of turbines, compressors, for such devices, we are not going to use it. Heat engines, anything. Okay. All right. Now you see that if we have entropies of inlets and outlets, then we can calculate the entropy generation. Okay. So when we look at the problem, this problem, you can see we have state 1 defined pretty clear, right? If you go to property tables, then you can straight away find the entropy at state 1. Are we all in agreement? State 1 can be easily found. Perfect. And then state 3, it says saturated vapor and temperature is given. Can we find the properties at state 3 straightforward from the tables? We know that it's going to be on saturated vapor line and temperature is given. So we can find this state as well using the property tables. So it's not going to be difficult. But state 5, we only know the pressure at state 5. But knowing only the pressure, we could not find the other properties. We need one additional property, something to play with, right? So as we want to calculate the entropy, that equation has entropy generation, that equation has some missing parameters. That's why we are looking into the other options, right? So the other equation, anybody, what can we use in addition to this? What can we use in addition to this? What are the other relationships that we can use? We can use first law. Excellent, sir. So we can use first law, and then we can find relationship between state 1, 3, and 5, right? Okay. So let's look into the solution altogether. So from continuity equation, we know that mass flow rate at state 5 should be equal to m1 and m3, the sum of m1 and m3, because point 5 is the only exit point here. So it should flow all the mass that came into the system. Therefore, m5 is equal to m1 plus m3. And if we apply the first law equation to the system boundary that we defined here, when we do that, you see Q is equal to 0, W is equal to 0, and steady state, and delta KE is negligible. Delta PE is also negligible. Then we can write the first law equation for the selected control volume as this. So now when we go to state 1 and 3, as we discussed earlier, we can easily find the properties from the property tables. So we plug in the numbers to the first law equation, and then we come across this line. So the y that you see here is from this line. So we define the ratio between m1 and m5 to be 0.62, and we call it y, right? And then it's important to note, if 0.62 or 62% of the mass that is going through the outlet is contributed by the turbine inlet, the remainder should be contributed by the compressor inlet, because then there's only two mass inflows. Therefore, if m1 is 0.62 times m5, then we can say that m3 is 0.38 times m5, or 1 minus 0.62 times m5, right? So if we divide the entire first law equation by m and substitute for the numbers, we can come across a value for h5. So specific entropy generation, like we don't have a parameter defined under that name, but entropy generation per kilogram, that is what we calculate here. Because entropy generation divided by a positive quantity, it doesn't really change the sign of the thing, right? Whether it's possible or impossible, what we are interested in seeing is whether it's positive or negative. In certain questions, you will be provided with the diagram. If not, you should be able to draw the diagram depending on the description. In case if you have not been provided with the diagram, then enough details will be provided for you to draw the diagram. Now, after finding H5, now we have two properties for the outlet: pressure and enthalpy. Now, using these two properties, you can find the final entropy, right? Because you have two state properties, enthalpy and pressure. So for ammonia, we can go into property tables. You know what? Like, let's go and see whether we can find this. Enthalpy is 1495. So let's try to go and find ammonia first. Ammonia property tables, saturated ammonia. This is going to be what is the pressure? 1.2 megapascal or 1200 kilopascals, and 1495 enthalpy. Okay, so let's try and go there. 1200, somewhere close to this range. And enthalpy, okay, this we have to go to the other table to find enthalpy. Okay, 1200. Okay, it should be somewhere here. And enthalpy value that we have is 1495. So 1495 is greater than Hg values that we see in both cases. So what does this mean? So this means that our substance is in superheated region, right? So now we go into the superheated tables. Superheated ammonia, so 1200 kilopascals, 1200. We look for the pressure. Okay, now we are at 1200 kilopascals. The pressure is good. Now we need to find enthalpy. The third column is enthalpy. So 1495. Okay, perfect. So we have 1495 0.4. So this is pretty close. So if you want more accuracy, 1495.4. It's exactly the same number. Okay, perfect. So now we can get the entropy value. S value, specific entropy 5.0564. So which we see here. And once we know the entropy value for state 5, we already knew the entropy values for 1, 3, and 3, state 1 and 3. And as discussed earlier, for using the entropy equation, you can calculate the entropy generation divided by M5, right? So we have a negative number as the answer. So which means that is going to be an impossible process, because entropy generation cannot be less than 0. For a reversible process, entropy generation is going to be 0. For any reversible process, any practical process, I'd rather say, it's going to be greater than 0. Under any circumstance, if you see a negative number for entropy generation, then it's going to be an impossible process. So don't mix these two things up. Entropy generation and entropy change are two things. Entropy change can be negative. It's fine. Two states, if you have state 1 and state 2 and you have two entropy values, and entropy change can be negative. But entropy generation cannot be negative. I have one more thing to highlight. In this question, we did not know the absolute mass flow rates, but we knew the ratios between the mass flow rates. So we completed this entire question just knowing the ratios, right? Sometimes it is the way we can solve a problem. Like, you use the given information in a smart way. Sometimes you will have the absolute mass flow rates. Sometimes you will have the mass flow rate ratios. So either case, you can solve the question. Okay. So now let's look into the other example. In this question, one type of a feed water heater for preheating the water before entering a boiler operates on the principle of mixing the water with steam that has been bled from the turbine. So basically it says this feed water heater mixes the water with steam, and then for the states as shown in the figure, calculate the rate of net entropy generation during the process, assuming the process to be steady flow and adiabatic. Assume the outlet flow rate of the feed water heaters to be 4 kilograms per second. Okay, so now the question asks the entropy generation. So we'll start with the entropy balance equation. So ds by dt equals q dot over temperature plus sigma mi si minus sigma me se plus sj. And assuming steady state conditions, this goes to 0. And assuming Give me 1 second to get another color. This goes to 0, and assuming adiabatic conditions, this goes to 0. So now what we need in order for us to find the entropy generation is the entropies at 3 states and the mass flow rates at 3 states. So entropies are already given, so we don't have to bother about that, but we need to find the mass flow rates. And M3 is given. M3 is given as 4 kilograms per second, but M1 and M2 is not given, right? From the continuity equation, we can say that M3 equals M1 plus M2. That is going to be one equation. And if we write the first law equation, then it's going to be adiabatic conditions and no work done, and the kinetic energy and potential energy differences, we can neglect those. So in that case, we can say that M3H3 equals M1H1 plus M2H2, second relationship. So we can pick this one as another equation if needed. So three unknown parameters, sorry, not three, but two unknown parameters and two equations to solve for two unknown parameters. M3 is known, so there's no point of adding this as an equation. We know the M3 value, right? After finding M3, then it's a matter of plugging in the numbers and calculating the entropy generation. So let's go to the next page and see how this is done. So this is the exact same steps. M3 is going to be the continuity equation, and then we write the enthalpy balance, and then with that one we can calculate M1 and M2, and with this information available we can plug in the numbers for the entropy generation and calculate the final number. Okay, so units are very important. So if it was specific entropy, then it's going to be kilojoules per Kelvin per kilogram, and rate of specific entropy, then it would have been kilojoules per Kelvin per kilogram per second. But in this case, we have this unit because it's the total entropy generation, not the specific. So we have this unit. So in the exams, please use the correct units and always mention the units. For those, you will get marks, and if you don't mention the correct units, you will lose marks. Okay. Take about 5-6 minutes and solve this question. So let's start the discussion. Now, at state 1, it says there's saturated vapor and liquid, right? Yeah, it is tricky. So a rigid tank of 1 cubic meter contains water initially at 120 Celsius with 50% liquid and 50% vapor by volume. Okay, so the temperature is given, and what can we say about the phase of this water at state 1? What can you say about the phase of water at state 1? it is definitely two-phase, right? So if it is two-phase, the pressure at state 1 is going to be Psat, right? So if we ever need the pressure at state 1, we can go to the property tables and check for 120 Celsius, and the pressure right next to it is going to be our pressure that we are interested. And then it says the volume ratio of liquid is 50%, and the same for vapor at state 1, right? Let's say for state 1, then we'll take the calculations here. So M liquid is going to be at 120 Celsius, 0.5 is going to be our volume divided by Vf, and M vapor is going to be 0.5 divided by Vg at 120 Celsius, right? So all these things happen at 120 Celsius. And then we can define X by M vapor divided by M total. So we have the X. This is about state 1. Okay. So with this step, we calculated the X. Now we have the quality of the mixture, and we have the temperature, and we know it is in two-phase region. Can we find all the properties, enthalpy, entropy, and whatnot about this state? Can we define state 1 properties? Okay. So now when we come to state 2, we know that it is a saturated vapor, and then that means we can go to two-phase tables and get Vg, Sg, Ug, whatever the values that we need, right? Can we find state 2 properties, all properties here? Perfect. So now there M2 is equal to total volume divided by Vg, and you can find the total water volume, total water mass left at the container at state 2. When we know that, like here we can, in the first step for state 1 we found the total mass in the system, and for the second step we found the total mass in the system. Now the difference of these two values is going to be the mass that left the system, right? So some portion of substance left the system as saturated vapor, and it says, the question says, only saturated vapor is going to leave the system, and until the pressure reaches 1 megapascal, pressure relief valve is set at 1 megapascal. So unless the pressure is 1 megapascal, then the vapor cannot leave the system. So that means once we reach 1 megapascal, vapor keep leaving the system, but the pressure does not grow any further. So it's always going to be 1 megapascal, and the leaving substance or water leaving the system is going to be saturated vapor at 1 megapascal. So now let's look into the solution, right? So as I mentioned earlier, the mass left the system is the difference of the mass at state 2 in the system, and minus the mass at state 2 minus mass at state 1 is going to be the amount of mass that left the system, right? So then if we apply the first law, then you can say there's no work done during this process, and the kinetic and potential energy differences are negligible, and there's no mass inflow rate, right? So delta Ke delta PE negligible, right? So that is one assumption. W equals 0, no boundary work or whatsoever work done during the system. And then again, no mass entered the system. It's just the mass left the system, right? So then that way, the total internal energy of the system, the difference of total internal energy of the system is going to be M2 U2 minus M1 U1. So this is very important. Most of the questions we solved involved steady state, right? But this tank is not in steady state because the mass is changing, right? Therefore, the total energy difference of the control volume can be calculated as M2U2, which is the total energy at state 2, minus M1U1, which is the total energy at total internal energy at state 1, which is equal to the energy added in the form of heat minus energy or enthalpy taken out of the system with the leaving mass. So are we clear about this first law equation? Any questions? It's very important you understand. So this, give me 1 second, this, sorry. This orange portion was assumed to be 0 in many questions, assuming steady state assumptions. But in this question, it is not 0 because the mass of the system is obviously changing. So we cannot assume steady state assumptions, right? The question asks us to calculate the heat transfer to the tank and show this process does not violate the second law, right? So we know all state properties. We know all state properties that we see here. U2, U1 already we know, right? We can calculate it from the, or we can find those from the property tables. And HE is also known because we know that we agreed the mass leaving the system is going to be in saturated vapor condition at 1 megapascal. So HE is known, and all the mass components we know how to calculate. Therefore, we can find the heat. We can find the heat from this equation, right? We can find the heat from this equation. And in order for us to find that, we'll go through the calculation procedure. Vf at the given temperature 120 Celsius can be used to calculate the total liquid mass in the system. Vg and the volume fraction of the vapor in the system can be used to calculate the final vapor mass. And by the sum of these two, we know that M1 or the total mass at state 1, and then we can calculate the quality of the system using vapor mass divided by the total mass, so which have the quality. And then once we have the quality, we of a two-phase region mixture, so it's a simple matter of getting UF and UFG, SF and SFG, or whatever the property values, and plug the quality and the property value to find the desired properties, right? So we can define state 1 like that. So after defining state 1, now we need to define state 2, right? The total volume V1, total volume of the system is not going to change because it's a rigid tank, and as it is saturated vapor at 1 megapascal, then it is pretty easy. We just go to saturated tables and get Vg, Ug, Sg values as our property values. And once we have the specific volume at this stage, then we can calculate our mass flow rate. Not mass flow rate, mass inside the system at state 2, right? And you know that at the first instance we had M1, at the second instance we had M2, and the difference between these two is going to be the mass which left the system, which we calculate here. right? And then we know that uh, the question said only saturated vapor can leave the system, and at the same time it said when it tries to exceed 1 megapascal, only the pressure relief valve activates. So we know that the leaving water should be 1 megapascal saturated vapor. So from that, we can get the enthalpy and entropy of the leaving substance. So now, after finding the property values, we can substitute those numbers in the first law equation to calculate the heat transfer amount. After doing that, we have to use the entropy balance equation to calculate the entropy generation, right? So for this system, we can say that entropy change is equal to the entropy added by the heat transfer plus uh, entropy left the system in the form of leaving mass with the leaving mass, and we don't have any inlet mass coming into the system, therefore we don't have to worry about this, and then Sgen. And from this equation we can calculate the entropy generation component, right? So entropy change of the system, again similar to internal energy, as the mass is changing, m2s2 minus m1s1 is going to be the entropy change of the system, and entropy taken out of the system is going to be MESE, and then this is the heat added to the system divided by temperature at which the heat is added, which is 120 Celsius, and we have to make it Kelvin before substituting here. So with this one, we get entropy generation as 120.4 kilojoules, and therefore it is greater than 0. The process satisfies the second law. This question gave us an opportunity to analyze the system where it is not steady. The conditions are not steady, right? Because steady state assumption was something very common that we used. But in this question, how do we know that this is not steady? Because it's obvious that some amount of water is leaving and no water is coming in. That means the conditions inside the system is going to change with time, right? That's why we did not use the steady state assumption here. Take about 3-4 minutes, and then we'll discuss the solution process. So this question says a piston cylinder assembly contains 2 kilograms of liquid water at 20 Celsius and 100 kilopascals. So state is clearly defined here, and it is now heated to 300 Celsius by a source at 500 Celsius. A pressure of 1000 kilopascal will lift the piston off the lower stops. Find the final volume, work, heat transfer, and total entropy generation, assuming the piston lifts during the process. Okay. So let's try to draw a PV diagram. So we start at state 1, and then from state 1 the pressure builds up, because until the piston starts moving the pressure builds up, therefore it goes up. So in exam, very important, the shape of the line. If it is a curve, make it a curve. If it is a straight line, make it a straight line. My line is not very straight at this point, but make it look straight if it is supposed to be straight. Okay. And then after reaching 1000 kilopascals, the piston start moving, right? If the piston starts moving, then the pressure is not going to build any further. So from 1000 kilopascal onwards, we are going to go like this. 1, let's call it 1A as in the solution. So 1A, and this is 2, right? And the pressure at this point is going to be 1000 kilopascals. And at state 1, T1 equals 20 Celsius, P1 equals 100 kilopascal. And the final temperature, T2, is given to be 300 Celsius, and we know that P2 is going to be 1000 kilopascal. So at the beginning, it was resting on the stops, and until we develop enough pressure to lift it up, we added heat, and we kept on adding heat, and once it reaches 1000 kilopascals, which is sufficient to lift the piston, and then after that, once we add heat, it tries to build the pressure, but it expands, so it keeps on going up. Yeah. And then it says a 500 Celsius source was used. Source temperature, let's say T source equals 500 Celsius. Okay. Find the final volume, work, and heat transfer. So state 2 is clearly defined. The pressure and temperature is pretty obvious. Therefore, we just go to the property tables and then find the final properties, right? And from the solution, because I have looked at the solution before, so I know that it's going to be superheated region. So the dome should be looking like this for 3 states that we have, right? And this is very important. If you are asked to draw your process indicating the phases of the states, then you have to draw the dome. Without the dome, nobody can gauge whether you have located your PV diagram properly, right? And then after you find the final volume, so it's just a matter of finding the area beneath the PV curve. Then you can calculate the work by calculating the area underneath the PV curve. From 1 to 1A, there's no work because there's no volume change. From 1A to 2, there's work that is highlighted in yellow as seen here. So that area is the work. And then we need to find the heat transfer. So in this case, we can find U1 and U2 easily because T1 and T2 states are clearly defined. So you can find U1 and U2. Then the mass of the system is given. Then if you apply the first law for a closed system, then it's going to be M into U2 minus U1 is equal to Q minus W. So work done by the system is already calculated. So we know that W, and U1 and U2 can be found from the property tables, and therefore you can find the total heat transfer, right? And similar to internal energies, entropies can be calculated too. So once you know the entropies, so you know that delta S of the system, or I would write M S2 minus S1 is equal to the entropy transfer due to heat plus entropy generation. As this is a closed system, there's no mass going in or out. Therefore, there's no need to account for that entropy because there's no mass transfer, right? And the temperature that we plug here is going to be the source temperature, right? So then we get the total entropy generation during this process. And if you look into the solution, you see that application of first law equation and then entropy balance equation. So then it's just a matter of calculating the properties and work and plug in the numbers. Then you come across the final answer. And the entropy generation is larger than 0. So what does this mean? Is this process possible, impossible, or reversible? It is irreversible. That means it is possible, right? It can happen. And also Alan is right, it is irreversible. So it does not violate the second law, right? It agrees with the second law. If it was a negative value, then it violates the second law. Okay. And with that, the good news is we have done completing our course content, and all the questions that we originally planned to complete were completed, and then all the theory components that we originally planned to cover was completed. Therefore, you can start preparing for your quiz 3 and finals. So quiz 3 anyways is not containing entropy, but for finals, so you have everything that you need to write your finals. So you have about 10 days to prepare for your finals. So I would highly encourage you to start preparations. And when you are doing so, I know that I'm a little further than the end time of the lecture. Give me 2 more minutes. When you are preparing for finals, if I were you, my strategy would be I would first go through the lecture examples, theory and the examples. I would bring the lecture slides and try to solve each and every question in the lecture slides first. That's the first thing I would do. Secondly, I would look into the tutorials and I will see whether we can solve all the questions in the tutorials. Thirdly, I will go to the assignments and try all the assignment questions.